Ladies and gentlemen, first thing I want to do is go through yesterday's activity, make sure that we have the essential information from this activity, the simulation that I was trying to get you to absorb. So you should have gone through and answered these questions, filled in your spectra, and submitted that electronically through the CAMI document. Before we come back and talk about number 6 here in a moment, I want to take a look at what I would say is the goal of yesterday's activity, is that you should be able to explain what the lines on an emission spectra represent. Those lines are labeled A through E down below, and you should know the difference between the ground state and the excited state for an electron. So let's start with our spectra. So if this was a true emission spectra, instead of being blank white in the background, this would all be blacked out back here, and the only thing you would see would be the very distinct lines of light on a black blank background. Okay, obviously I can't show blue on top of black on my paper here, so that's why it's just empty back behind there. I want you to notice the wavelengths, these nanometer numbers down here below. They represent the wavelengths. Okay, and remember, all waves travel at the same speed, the speed of light. So the electromagnetic radiation, as the waves get more compressed, the frequency goes up, and then you get higher energy. So if I asked you to take a look at these emission spectra, what I need you to realize is that each one of these lines, A through E, each one of these lines represents the energy that is released, when an electron from an excited atom, meaning we've put it over heat or we've passed electricity through it, the electrons jump from their normal location, we call that the ground state, to a higher energy level. When they jump to the higher energy level, that's what we call the excited state. So these two blue circled electrons are where these electrons went. They jump up to the excited state. They jump out of their normal energy level to a further energy level from the nucleus, but they can't remain there. So the energy that they used to jump out to the excited state, when they drop back down, when they fall back down to the ground state, they give off light. And depending on the size of the jump, bigger jumps would release more energy and give color over in that blue-violet range. Smaller jumps would release lower amounts of energy, and they would be in that red to orange range. Okay? So if we are asked to rank the lines above by increasing wavelength, you would go from low nanometers to high nanometers. It would just be A through E. If we're asked to do a ranking by energy, how does the energy increase? It would be the opposite of that. So red light down here is the lowest energy light that we can see. Obviously there's infrared and microwaves and things like that. And then above violet, in the ultraviolet, the gamma rays, the X-rays, and things like that, we have higher energy. So each of these lines represents a drop from an excited state back to a ground state. The bigger the fall, the higher energy light that's given off, and the more towards the violet-blue end of the spectrum it is. The smaller the jump, and the smaller the fall back down, the lower energy light, the red and orange colors that we'll see. One of the questions you were asked to take a look at was in number 6, asked you hypothetically, what would happen if we took two elements and combined them together in the same sample and then excited them. So we're just going to use two generic elements. We're going to use element A and element B. So if we took element A all by itself, we heated it up to the point of glowing incandescence, or we passed electricity through it to the point where it started to give off light, this would be its emission spectrum. Okay? Element B, same thing, by itself, would have these 5 lines. What the combination, if we put both of those together, what we would end up with is a superimposing and overlapping of element B spectrum over element A. So imagine that these were on like a piece of transparent plastic, and we could take this one and set it right on top of that one. The result would be this down below. You would take the 3 lines from A plus the 5 lines from B, and they would all keep their position, and they would all just stack together. This would also take the visible color that is given off by an element, and it would mix them together. So let's say that this one was blue, and this one looked green. Blue and green, put them together, we would end up with a kind of a turquoise type color. Okay, so mixing elements together creates a superimposed, combined, almost an addition of spectral lines added on top of each other. Now, as we go through again, make sure that this is completed and submitted electronically. The activity today that I want you to work on is building an atom. So you're going to use your periodic table to complete this document. So I would print this document out if you have the ability to do so. If not, don't fret over not being able to print it out. Instead, just answer the questions in order on a piece of notebook paper, and you can take a picture or scan that and submit that. Just for ease, I would say these would be the symbols I would use for protons, neutrons, and electrons. For protons, a plus sign in a circle, neutron a zero in a circle, electrons a negative in a circle. And just draw your nucleus, so create your nucleus first, and then draw dotted lines for the energy levels. There's only going to be 1 or 2 for these first 10 elements. And then place the electrons on your model in the same way that they are shown on this simulation. So you're going to open the link to the simulation. You're going to click on Atom. You can play the games later if you want. And you're going to work through the first 10 elements. My suggestion would be to click on this stable, unstable one, because what it's going to allow you to do is if your ratio of protons to neutrons gets off of what's on the table, it'll kind of shake around and say that it's unstable. Use your atomic number, the mass from the table to round to get a mass number, and use those values for neutral atoms to build your atoms. So let's build hydrogen together. Hydrogen has an atomic number of 1. So we're going to take 1 proton, we're going to click, drag that into the nucleus, and it tells you it's hydrogen because it has a 1 proton, and it's going to show you that. Okay? We don't need any neutrons for hydrogen. No neutrons, because the mass number is 1 and the atomic number is 1. So that means 1 minus 1, mass number minus atomic number to get neutrons is 0. We know that we want it to be neutral, so to balance out the positive proton, let's click and drag an electron up here. And pay attention to what happens. If I put an electron anywhere in the cloud, it's automatically going to go to a certain position. That's what I want you to focus on as you're drawing these out and creating these simple atomic models. Look for the patterns of where did the electrons go, how do they fill in these 2 energy levels. Okay? Once you get to the end of those 10 elements, you should have your your simple atomic models drawn, and then answer these 3 questions. I'd like you to have that submitted before I see you for our conference on Thursday. Okay? Please shoot me an email if you have any questions, if you need anything. I will see you in conference on Thursday.